Hello everyone and welcome to We Meet at Digital Days. My name is Marie-Therese Kohl and I will moderate this presentation. We are very pleased that you took the time to participate in our virtual conference. The topic of this presentation is connector temperature rise and derating. Our speaker is Stephan Bächle. He will hold the presentation and will answer your questions. But before we start, I would like to point out one thing. You will be muted during this presentation. This means that you cannot ask questions via microphone during the presentation. But nevertheless, you have the opportunity to ask questions during the presentation at any time via the chat function. And you can find the chat function in the webinar control panel. This presentation will be about 30 minutes long. The chat questions will be answered in a Q&A session following the webinar. There are about 5 to 10 minutes in addition scheduled for this. And if we are unable to answer all of your questions within this time, we will answer them via email afterwards. And if you still have any other questions left, just mail us at exhibition@w-online.com. We will try to answer all of your questions promptly. At the end of the presentation, you will be asked to participate in a feedback survey. We would be pleased if you take the time to fill out the survey and help us to improve our event. You will also receive the link to this presentation in the next few days. Also, the recording will be available at our website shortly. But now I will hand over to our speaker, Stephan, and I wish you an exciting presentation.
Yeah, welcome to our Digital Days. My name is Stephan. I work in the company now since 11 years as a field application engineer, and I'm responsible for customers in the south of Germany. But I'm also doing some international training as a technical trainer in the company. Today, I've got a special topic for you, connector temperature rise and derating. First of all, thank you that so many people join our webinar today. I'm really happy about that. You do not have to note anything because you will receive a download link for the presentation after the presentation is done. And I also will switch out my camera again during the presentation so that you are able to concentrate on the presentation. And after that, I will switch it on again for the Q&A session so that we can talk together in a proper way. Okay, I think we can start with the topic now. The topic is called connector temperature rise and derating. So, as field application engineer, when you're out on the field, you see a lot of applications. And sometimes you also see applications you do not want to see. And what you see here on the picture is such an application. It was done by a big manufacturer of steam cleaners here in Germany. And it is a wire-to-wire connection with a terminal block you can see here inside. One moment, I will switch over to a laser pointer so you have a better view on the pointer here. So you can see this is a terminal block suitable for 20 amps, and in this application was a current flow of exactly 20 amps, but it didn't work. The connector got too hot, as you can see in the picture here. Why? Because there was a closed box around the connector and there was no possibility to dissipate the heat. And to avoid issues like that, I've got a presentation today for you regarding derating. So the agenda for today, first of all, we will have a look how a manufacturer like Würth Elektronik finds the right working current when he is designing a connector for power. The second point will be the consequences of a too high temperature. Consequences of a too high temperature, we have to know what happens when the temperature gets too high. So therefore, we have to respect a few things I will show you there. And the third point is the temperature rise rule. We have a look at the temperature rise rule itself. Then we have a look how we can dissipate the heat again, how heat is dissipated. We have two possibilities for that. We can dissipate the heat in the cable we have on our terminal block, but we can also dissipate the heat a little bit in the PCB. And we will have a closer look at this point, how we can do that. Then we have some tricks for you, how you can optimize your application when you have high currents and a connector in between. And then we will show you how to establish a proper derating curve so that you are sure to use the connector always in the right terms. And at the end, I will show you some pictures of connectors where the derating was not respected. First of all, the basic connector use. We talk about the same connector as we saw in the picture before. It is called a terminal block. This terminal block is made out of plastic material, like in this case it's PA66, a polyamide. And we have also some metal parts inside. And this is a wire-to-wire connection. It is suitable for 20 amps. Why is it suitable for 20 amps? It's just because of the size of the cable we can put inside. So the biggest possible cable we can put inside is AWG12. And with an AWG12, we are able to handle 20 amps. That's written in the UL files. And so we use the 20 amp for this connector. Regarding the temperature for the connector, we have to have a look on we have to take in consideration the so-called RTI. RTI means relative thermal index. It's related to the plastic material. And in this case, from PA66, the relative thermal index is 125 degrees Celsius. At Würth Electronics, we always use a safety margin of 20%. So we decide the highest possible temperature for this connector, not to destroy it, is 105 degrees Celsius. What's the meaning of the RTI? The RTI says up to the temperature which the RTI gives, the connector can be used normally. When you go higher than the temperature in the RTI, the plastic material will age faster. And this is what we want to avoid. So we choose the right RTI and the right temperature for our connector, in this case, 105 degrees Celsius. So we have a look at electricity and temperature rise itself. When we have a connector, it behaves also like a resistor. You know there's a little bit of resistance inside of the connector regarding the crimping contacts, regarding the connection zone and so on. And all this adds, when we all add those resistance, we come to a resistance, a total resistance of the connector, and so he behaves like a resistor. And when we have a resistor, it's lying in our room, for example, then it has a temperature, our room temperature T. Next step, when we put power on the connector or on the resistor, we put some current inside. Then we have the effect that the current is always heating the resistor additionally. That means we have to add the temperature from which is existing at the room temperature to the delta T we produce with the current. And that's the same principle as we have on an oven, in electric oven in our houses. So how can we design our connectors and how can we test our connectors regarding the temperature and regarding the current? Therefore, we use the so-called temperature rise test. It's a standard. It's written in EIA 364-70. And we have to use a 3-pole connector. This is written in UL 1059. This standard we use for the temperature rise test. And the working current has to be put in series so that at every point the same current is. Then we apply the current of 20 amps in this case, and we have to reach a stable temperature. We have to do 3 measurements there each 5 minutes, and the temperature swap should not be higher than 1 degree Celsius. And then at the hottest point, the UL says that the delta T, or the warming of the connector, must not be higher than 30 Kelvin. This is written also in the UL 1059 standard. When we look at Europe and we use the VDE standard, it's a little bit different. It's not that conservative as the UL standard. It says a temperature rise of 45 Kelvin is allowed. So when we have our application to design regarding UL, when we want to sell it to the US market or the Canadian market, we have to respect the UL. So 30 Kelvin is the maximum temperature rise of the connector, which is allowed in this standard. How does this work? We have a chamber where we do the measurements inside, and we have some thermocouples we stick on the wires and on the connector, and then we can measure the temperature in a proper way. Here you can see how this is done. We have our test method at the hottest point. It's in the middle of the connector at pole 2, because the heat cannot go away to the right and to the left. It's just in the middle. So this is the hottest point, and we put our measurement point exactly there. And then you can see the electric assembly. We have the AWG12 cable, and it's 1 meter long, and this is also written in the standard. And then we do the temperature rise test and put on the current of 20 amps and see what happens. So UL says that the maximum rising temperature should be 30 Kelvin at the hottest point. The hottest point we see in the picture here at SP1. There we did also the measurement. And the measurement said it's 46.5 degrees Celsius. And before we had an ambient temperature around 21.7 Celsius, and that means the temperature rise, the delta T was 24.8 Kelvin. And 24.8 Kelvin is under 30 Kelvin. That means it's totally okay to specify this connector regarding 20 amps at 105 degrees Celsius. So now you saw how a connector is designed at Würth Elektronik, and now we have a closer look on the consequences of a too high temperature, because we have to know what happens there when we have a temperature higher than allowed. First of all, have a look at the metal parts. And there, when the temperature goes higher, we increase our corrosion speed of the metal, of the plating. When the corrosion speed is getting higher, it naturally increases also the contact resistance. And when the contact resistance increases, this increases the temperature again. And when the temperature increase the corrosion speed. So this is really a vicious circle. We have to take care about that. As you can see on the table on the right side, each 50 degrees Celsius more, we have an additional resistance of 20%. And this leads to increase of corrosion speed. Second point we have to have a look at is the plastic material. This plastic material accelerates aging regarding the color, and regarding it, if it gets too hot, it's also a little bit brittle, it's more breakable. And this is related also to the relative thermal index. We've spoken before about this topic. And as you can see, for the polyamide, it's 125 degrees minus our security margin is 105 degrees Celsius for our connector. So we have to respect this because of the mechanical strength of the plastic material and of the electrical properties of the plastic materials. The third point is the metal relaxation. And also the metal relaxation goes a little bit faster when the temperature is higher. So you can see the graphs here on the right side. If we have a temperature of 20 degrees, after 10 years, you will see not that big metal relaxation. But if the temperature is about 150 degrees, the relaxation becomes earlier and much higher than in room temperature. That means we also have to look on the metal relaxation. This leads us to our temperature rise rule. We also can calculate the whole thing. The temperature rise rule is quite easy. It's related to the Joule's law. It says power is the resistance multiplied by the current in square. And this is a little bit dangerous, because when you have double current, you have 4 times higher temperature rising. Let me give you an example. When we put 50 amps on this connector, it gives us a delta T of 15 Kelvin. This is quite okay for our connector. As you can remember, we talked about 30 Kelvin is good for a connector, not higher than 30 Kelvin. But when we put on the same connector the double current, means 30 amps instead of 15, when you take the formula on the right side, this leads to a warming of 60 Kelvin. So that means 4 times higher warming on our connector systems. And this is no more suitable for our connector, and the connector will burn. So take care about the temperature rise rule. It's always the square of the current, which we have to respect. Gives us a warming 4 times higher. Is this really true? I can tell you a lot of things, but we can also do some measurements. So we did here a temperature rise test again with 20 amps at our connector we saw before. And you see here the calculations done from the 20 amps we did one slide before. And now the graph of the measurement, it's exactly the same graph. So this is true. If you have double current, you have 4 times more warming on your application. What do we have to remind on this point? Each resistance releases heat under current. That's true because of the Joule's law. Working current has to be designed with, regarding UL, a maximum temperature rise of 30 Kelvin, regarding VDE, a maximum temperature rise of 45 Kelvin. And we have always to respect the maximum working temperature because of the plastic material, because of the aging of the metal materials inside our connector. Fine. So the most important thing, temperature rise is always proportional to the square of the current, not directly to the current, to the square of the current. So now we will have a look how we can transport our heat away from our application. And therefore, I will give you first of all a little example, which you all know, I think, like a fire you can do in the garden. And when you have a fire and you come closer to your fire, you will feel a little bit warm. And this is because of the phenomena of radiation. Radiation is heat dissipation through light emission. Light frequency depends on the temperature. And this is the principle of the thermal camera, for example. And it's also the way how the sun heats the earth through billions of kilometers of frozen vacuum. That's the point of radiation. But we have more possibilities to dissipate the heat. For example, convection. Convection is the dissipation through the air around the heat source. Natural movement of the air will go up. The hot air will go up, the cool air will go down again, will be heated up and then come up again. So this is called convection. And we have a third possibility to dissipate the heat. And this you can find out if you put, for example, a metal bar into your fire and touch it on the other side. And you will see it is getting very hot very soon because of conduction. Conduction is related to the material you put into the fire. And in this case, we can have a look on our material in our wires and also in our PCB. We will see the importance of the wire length in the presentation in a few slides. So we do not have a fire in our application, fortunately not. We have a connector and we have a cable and we have a PCB. So we have to decide how to dissipate our heat over the cable or over the PCB. Those two possibilities we have. And there's also the 3 points we saw before: convection, radiation, and also conduction. Conduction along the PCB and conduction along the wire. Let's have first a look on the heat in a cable. There we have some tables which cable is suitable for which current. And there we have a UL table, the UL486. We have to respect when we want to sell our applications to the US market, for example. And this standard says for 20 amps, we can use a maximum AWG cable size of AWG12. When we look at the VDE, it's a little bit different. There we have to use the IEC table in the middle here. It's not that conservative as the UL table, as you can see. And therefore, when we have AWG12, which is around 3.3 square millimeters, we can use in between 17 and 24 amps for VDE. But we have another VDE table here on the screen. You can see VDE 0100, but this is something completely different. Please do never use this table in electronics. This is only for cables which are in free space without any insulation. For example, the power cables which come to your houses without any insulation in the free air. There we can use a bigger current for the square millimeter cable than for other cables in our electronics. That means we have to use the UL table or the IEC when we want to sell our product to Europe. The resistance is quite easy. In a cable, it just depends on the square size of the cable and on the length of the cable, as you can see here in the formula, and of course the material resistivity. And in a cable, we have the copper. We use the material resistivity of copper. So we did a test. We have a 50 centimeter long wire, AWG12, with two thermocouples sticked on the copper conductor directly. And we will put on the 20 amps which are allowed for the AWG12. And then we did some measurements at different points. And this is the result. When you have a wire size of AWG12, you get a maximum additional warming of 11 Kelvin, and 11 Kelvin is below 30 Kelvin, so this is okay for our connector and for our whole system. So delta T decreases proportionally to wire size, and wire heats less than the connector itself. The connector must be lower than 30 Kelvin. The wire is lower than the connector. It's around 11 Kelvin in this case. But what's the right length of the cable to dissipate the heat out of the system? This is something we had to do another test again. We took the same cable to AWG12 with 20 amps again. We have the TBL plug inside again with 3 poles and different wire lengths and 2 thermocouples in 2 TBL clamps. So we use a long wire around 1 meter, and we use also a very short wire around 2.5 centimeters. And the result you can see in the next table here. You can see that the cable length in centimeter reduces the temperature rise up to around 10 to 15 centimeters. That means a cable longer than 10 to 15 centimeters has no effect anymore on our system. Is it shorter than 10 centimeters? It gets warmer. It's not possible to take the heat out of the connector again. So the ideal length of the cable is between 10 and 15 centimeters to dissipate heat out of the application. This is something you should remember when you do application with high currents and connectors. 10 to 15 centimeters, the ideal cable length. So let's bring it together. We have to optimize length for the heat dissipation to 10 to 15 centimeter. Less will increase internal connector temperature above the 30 kelvins, which are allowed. And yes, more is useless for thermal dissipation because it has no effect anymore on our system. So what do we have to remind? The copper wires itself heat less than our connectors. And the wires are used to dissipate heat out of the connectors, and the optimized length is 10 to 15 centimeters. Okay, some additional tricks for you. We talked about 30 Kelvin is okay for a 3-pole connector, but what about polarity when you have more than 3 poles in the connector? The working current is only tested at 3 poles. Should we decrease the current with more? What do you expect? A curve like this? So the more polarity you have, the more warming you have. We did a test and found out that it's not completely different. So reality is the blue curve you can see here. Because of the safety margin and because of the radiation of the bigger surface of the component, we have a bigger radiation, and then there the heat gets dissipated a little bit better with the high pole connector, and this leads to the same situation with the 3-pole connector, and that means at the end you can use this derating curve for every poles of our connectors. Doesn't matter if you have a 3-pole or a 20-pole or a 10-pole connector, you can always respect the same derating curve. Because of the security margin, working current can be used for any number of poles. What about the mating cycles? Should I decrease the current after some mating cycles? We did a test with our mini modules. They are specified with 25 mating cycles. And what you can see here, the lines are the contact resistance. And as you can see, it doesn't rise that much. So we do not have to respect the mating cycles regarding the current when you choose the connector for your application. What about the tightening torque? It's important to use the right tightening torque. If you use a higher tightening torque, get you a lower resistance then? No, you don't. Also, we did a test here, and as you can see, up to the optimum tightening torque, there's something happening. But when you at the point when you reach the optimum tightening torque, in this case 0.4 newton meters, it stays the same. So the resistance doesn't go down more when you screw harder. So it doesn't make sense to screw harder. You only destroy the system. Please use the recommended tightening torque in the data sheet. So now a connector in a closed box, as we saw on the first picture. We did a test putting our connector in the closed box with an AWG12 and 20 amps. And this is what happened. The time for the stabilization took much longer than without any box. So there's no possibility to bring the heat out of the box. Thermal energy is stored in the box, not enough exchanges. Then we put some holes in the box so that we have some exchanges, a closed box with some holes, the same test again. And you can see it gets a little bit better and the time for stabilization gets a little bit lower, but it's still higher than without a box. It's a little effect that we have when we put some holes in the box. What brings us a little bit a better effect is to put the wires outside of the box. We have the closed box and we put the wires outside. As we saw before, we can dissipate our heat through the wires, 10 to 15 centimeters, for example. We have 10 centimeters cable out of the box here. And you can see it's getting better and better with the connector temperature rise and the connector temperature rise stabilization time. And the last test we did, okay, external wires add the conduction effect, the better effect than the holes in the box. The last test we did here is 15 amps instead of 20 amps, just reduce the current a little bit. And this was the best solution we can do. So the best effect is to reduce the current if possible, or to take a connector which is suitable for higher currents than the current is in your application, and then you're always on the safe side. The best way is to decrease the current directly. When you look at the PCB, there might occur a question, does thermal relief increase the temperature rise? This is also what we tested. We had a PCB with a terminal block with 57 amps, and we had a 16 square millimeters cable. And as you can see here, the difference with thermal relief and without thermal relief is not that high. It's just around 1 or 2 degrees. That means thermal relief has no significant influence on the temperature rise. How can we cool down our PCBs? We did a test with the vacuum PCBs with 100 amps, horizontal and vertical PCB. So if you have the possibility to store the PCB vertical in your application or horizontal in the application, this is really a difference. As you can see here, the vertical PCB is cooler than the horizontal PCB. And when you use a fan, you have exactly the other way around. The horizontal PCB gets cooler with a fan than the vertical PCB. That means at the end, vertical position for a PCB is naturally cools down the components, and fan is obviously a good idea if it's necessary and if it's not enough without a fan. So the most important point for this presentation, how can we come to our derating curve? There are 2 derating curves from UL and from VDE available. I will show you how this works. We have to look how we can decrease our current when the ambient temperature increases. Maximum connector temperature, a delta T is maximum 30 Kelvin, and the delta T is proportional to the current in square. Let's have an example here. This is a wire-to-board connector. It has an operating temperature up to 105 degrees and a current maximum of 7 amps. And here we have the UL derating curve. And now when we have to look at which graph, we have to look at the black graph here because it's for 105 degree maximum temperature. And now I want to know which temperature I can put on the connector which current I can put on the connector when the temperature is rising. and you can read it just out of the graph here. For example, if you have a temperature rise to 90 degrees, we can only apply 4.9 amps, 70% of the current. And this is how, if you respect this derating curve, you never will have troubles with your connector. And the same you can do with the VDE if your application is for the German market or the European market. We have also a VDE derating curve. Here we have another example of a terminal block. This one is suitable for 24 amps regarding the VDE certification, and it has a maximum temperature of 120 degrees. So we have to look for another graph here, the gray graph, 120 degrees. And the same situation here. When I reach 90 degrees, I have to reduce my current to 21.1 amp. That means 88% of the current can be applied at 90 degrees. And there you can perfectly read out the maximum possible current you can apply at your temperature, which you reach in your application. I think this will help a lot to avoid pictures like the first one we saw in this presentation. So what to remind, the number of mating cycles has no influence on our delta T. If we screw hardly above the tightening torque, it has also no effect on our delta T. And when we decrease current with the derating curve, when we are at the close maximum operating temperature, it's the best way to go with the application. Use the derating curve. So at the end, I promised a few pictures of a connector where derating was not respected, and I will show you this in a few slides. It is a so-called MPC4 connector. It's a wire-to-board connector, and it's also possible to do a wire-to-wire connection with it. It has crimp contacts inside, and it's suitable for maximum 9 amps at 105 degrees Celsius. And what we did, we put 3 times higher current on it, more than 3 times higher. We used 35 amps. And as you can see, the plastic begins to melt, and the plastic is dropping away. We have a temperature at the middle of the connector of 258.2 degrees Celsius, and the plastic is melting, the plastic is dropping, but the connector is not burning. And this is very important when we have to use our connector, for example, for glow wire applications. So no fire. This is what we want to avoid. How can we avoid it? We have to create a thermal exchange with outside. So now I'm at the end of my presentation, and I hope you could enjoy it. And now I'm here for the questions you have. I will also switch on my camera again. One moment, please.
Great. Thanks, Stephan, for your interesting presentation. As already
You're welcome.
mentioned, you have now time to enter your questions, so feel free to ask what you want to know. Maybe one first question. I want to sell my final application to Canada. Which standard do I have to respect?
If you want to sell the application to Canada, you have to respect the UL standard. The UL standard has the same values as the Canadian standard, and sometimes if you buy a connector, you can also read CUL US, and this means it's tested for both countries, for the US and for the Canadian market. So use the UL table and the UL standard, please.
Sounds good. Thanks. Another
You're
question.
welcome.
Does maximum operating temperature means at max current rating in datasheet?
Maximum current means maximum current in datasheet. Yes, right. Maximum rating, which is given in the datasheet. And then you have to respect the derating curve, and then you are on the right way.
Okay, perfect. Another question. Which connection has a lower resistance, spring clamp or screw system?
This is really hard to answer. Normally, the screwing system has a little bit lower resistance because of the size of the screw. The screw is a little bit bigger than the clamp inside of a connector, so we have more connection space, and this leads to a little lower resistance. But this choice I would make because I would think about, do I have some vibrations in my applications or not? Because if you have vibrations in the application, you should not use a screw connector, because a screw can remove again when vibration occurs on the application, and this can absolutely not happen with a clamp connection.
Great, thanks a lot. Another question.
You're welcome.
Is it possible to split current over a higher polarity?
Yes, this is a principle possible. You can split it over when you have a current. Let's go for an example of 20 amps, and the connector is suitable for 10 amps. You can take a 3-pole connector and put the 20 amps over the first and the third pole, for example. You should have one pole in between, just to give the system a possibility to cool down a little bit.
Thanks. Another question. Is the maximum delta T still the limit, even if the ambient is colder, considering the flattening curve?
No, it is always the limit. Yes, also when the beginning temperature, the room temperature is lower, but you can have more. Yeah, you can put more current on the connector if the room temperature is lower, to reach the maximum temperature of the connector.
Great. Another question. Which influence has the volume of my box or housing?
This has really a great influence on the application, because the smaller the box is, the less possibility we have to dissipate the heat. So if you have the possibility to design your box bigger than before, you should do it. The bigger the box, the better the way the temperature can be transported away, the better the dissipation of the heat.
Thank you. And maybe one last question. When I have a PWM signal on the wire, how do I calculate the temperature rise?
Oh, this is a really good question. There I have to do a little bit of research about it. So I would answer this in an email, if it is okay for the customer. So it takes a little bit research in advance. Sorry for that. I will write
Sounds
an
good.
email. Please look for the email address, and I will write an email for that.
For sure. And if there are more questions left, we will also answer them via email afterwards. So
Sure.
thank you very much for your attention, and I hope you enjoyed the presentation. The next presentation topic is Red Cube, everything you need to know to handle high currents on your PCB connection. So this session will be start at 3 p.m. and hopefully see you there. Bye.
Thank you for joining. Bye-bye.